All right, so this is going to be a video about exponential functions. It's going to be section 4.1, the first one of the course. If you have any questions about anything in this video while we're going over it, make sure you timestamp it, pause, make sure you get the time so then when you can email me, ask questions if you got any. All right, let's get going with this. Before we start exponential functions, let's talk about linear functions first. So here's going to be like a mini linear functions review. You should know this already, otherwise you would have never made it this far in math. So this should just be a nice little review for you. So linear functions have the following form as listed right here. So f of x is equal to mx plus b. You've also probably seen, where f of x is the same as y, so you can just say like y is equal to mx plus b. You've probably seen it that way as well. Okay, m is the slope, if you recall, while the b is the y-intercept. So if you plug in x for here, you get the y-intercept, which is b. The important thing to understand with linear functions is that their rate of change is a constant. Okay, whatever the slope is, that's the rate of change. So what that means is every unit increase of x, f of x changes exactly by that value. So, as an example, if the m is 2, every single time we have x increase by 1, the y value, or the f of x value, which is the same as the y value, increases by 2. So if the slope was 3, if you increased x by 1, the y would increase by 3. If the slope was negative 2, if you increased x by 1, then f of x would increase by negative 2, or it would just decrease by 2. Okay, that should be all a review. So linear growth is additive. So what that means is you always add the same amount each step. Each step up of x by 1, you're adding whatever that slope is. Okay, here's an example. Population grows by plus 100 each year. So whatever the year was, the next year that goes by, your y value, which in this case is population, increases by 100. So the most important things that you need to understand on this is that it's additive, it's linear growth throughout. Because we're going to compare this to exponential functions. Okay, exponential functions have a completely different form. In this case, the form is the f of x equals a times b to the x power. It is important to note that a cannot be equal to 0, because if a was equal to 0, your f of x would just be equal to 0 the entire time. That's not exponentially doing anything, it's just a constant. So a cannot be equal to 0. A is also known as the initial value. We're going to be talking about this a little bit later when we do some example problems. So you have to understand that a is the initial value. If you put 0 in for x, this whole thing is going to become b to the 0 power, which means you have that a value. It's the initial value. So when x is 0, that's the initial value of whatever that a is. B has to be greater than 0, okay? So this base of the exponent right here, if you notice x is in the exponent, b is the base of that. B has to be positive, and it cannot be 1. Okay, if it was 1, then your f of x would just always be equal to a, because you'd have 1 to the x. Well, 1 to anything is 1. So it would just be a times 1, which means f of x would always be a. So again, you have a constant function. We don't want a constant function, we want an exponential function. So b has to be positive, and it cannot be 1. So that's the only positive number it can't be. It could be anything else. It could be 0.999, but it can't be 1. It could be 2, it could be 3, it cannot be negative as well. So the rate of change is not constant, it's not constantly growing by a specific value. Instead, it's proportional to the current value. Now what does that mean? That means that the function is growing or decaying by a fixed percentage or a multiplicative change. Okay, you're multiplying it by something, and that's what it's going to grow by. For example, if the base was 1.05 and the initial value was 100, this would mean this b is 105%, which means a 5% growth each time. So it's like you're multiplying, it even says it right here, each step multiplies by 1.05. That's why it's an exponent. An exponent, whatever that number is, that's how many times you're multiplying it. If you compare that to linear functions, which we just went over, that was adding. So the big change with exponential is that you're now multiplying. So the exponential growth is multiplicative, okay? Repeated multiplication, just like before when we were multiplying with the y equals mx plus b, the multiplying was really just repeated adding, because that's what multiplying is. So the other one was repeated adding, this one's repeated multiplication. The population doubles every year. Okay, it's not going up by 100. The other one was just plus 100 each year. This one, it just doubles. Whatever it is, it's proportional to the next one by 2. So it just multiplies. The population was 4. The next year it would be 8. The next year would be 16. It just doubles each time. You're not adding a specific amount. You're multiplying by a specific amount. So that's the difference between exponential and linear. Let's go further deep dive into this. This slide just shows a bunch of key differences between the linear and the exponential. We just talked about all of these, but just again, the form is completely different. And notice the form when it's side by side. The rate of change is constant because you're just adding that slope each time. This one is proportional. Okay, the growth type was additive with the same difference each time. You're always adding 2, you're always adding 3, you're always adding -1, whatever it is. The other one is multiplicative. Okay? Linear is a straight line. Exponential has a curve. We're going to talk more about what this graph looks like in the next video. Long-term behavior, it increases steadily by the same amount each time. This one increases rapidly because you're multiplying by a value. And multiplying is going to grow a lot faster than adding. So that's why exponential is going to grow a lot faster. All things considered. We're going to talk about that again in the next video. All right. So just kind of repeat myself again here. What an exponential function is, it has this form, a times b to the x. A is non-zero, and it's called the initial value. If it's 0, then you just have a constant function. B is any positive number, but b can also not be equal to 1. So any positive number except 1. The domain is whatever you can plug into a function and get a y value out. In this case, you can plug any number in for x for this function, for an exponential function, and you will always get a value out. Therefore, it is a function. It passes the vertical line test. It's a function. The range, I'm not going to worry about so much. It's based on the a value. You can kind of read it there, but we're not going to be doing problems with it or anything like that. The y-intercept is if you plug the 0 in for x, you get the y-intercept. It's always going to be a. That makes it easy. The horizontal asymptote is always going to be y equals 0 for this form. And we'll talk about that in the next video. Let's do some example problems for this section. Okay, some of this stuff might seem easy, but it does escalate pretty quickly as we go on to further sections. So make sure you have a firm understanding of this. This first one, which of the following equations are not exponential functions? Okay, so this first one here, f of x, if you notice we have a positive base that's not 1, you have x in the exponent, this is an exponential function, but we are looking for not exponential functions, so this bullet point is not one of the answers. The next one, g of x equals x cubed. Okay, this time x is in the base, so that's not exponential, and then we have a constant as the exponent. It should be x in the exponent instead. So this right here is actually going to be a cubic function. I'm going to write that in. It doesn't say to do that. I'm just doing that for fun. But it's not exponential. It's cubic. Now, on the other hand, if we had some second g of x function and it said 3 to the x, this is now an exponential function. Okay, because it's 3 to the x. It's got a positive base that's not 1, and the exponent is x. So that would be exponential, but this original g is not, so that's what we're looking for, is the not, so that bullet point will work. H of x is equal to 1/3 to the x, okay? The exponent is between, so the exponent is positive and not 1, so that works, and x is the exponent, so this is an exponential function, which means it's not the answer. The last one, we have -2 to the x power. The base is negative. So right away you should know that it's not an exponential function, which means it is actually the answer we're looking for because we're looking for the nots. These two bullet points are not exponential functions. So that's the first example problem. Make sure you understand that. It might seem easy, but I've seen people mess it up on quizzes and tests before too, so make sure you understand that. Okay, evaluating exponential functions. Okay, this is going to be something you're going to have to do. You did this before with linear functions, so it shouldn't be too big of a stretch. In this case, we're looking for f of 2. So f of 2 just means wherever the x is, we replace it with 2. So that means this is going to be 5 times 3 to the 2 plus 1. Okay, so that 2 plus 1 is obviously going to be 3. And then you're going to have 5 times 27, which is 100 plus 35. So 135 is going to be the answer for this. And I will highlight it. Okay, so it says evaluate f of 2 without using a calculator. That's what I just did. Important reminder in case you forgot how to do this. It's just wherever there's an x, you replace it with a 2. If it said f of 3, wherever there's an x, you replace it with a 3. If it said -1, wherever there's an x, you replace it with -1. That's all it means. Okay, so make sure you understand how to do those. You'll see them in your homework. You'll also see them in the quizzes and tests. Okay, example 3. Now we have a word problem, but I want you to kind of see that it's really basically the same thing we were already doing. If you know what an exponential function is, you know the form, it shouldn't be that big a deal. Evaluating a real-world exponential model. At the beginning of this section, we learned that okay, so I got this from the book, so that's why it says in the beginning of this section we learned that. If you didn't read the book, you didn't learn that necessarily yet. But anyway, that's the population of India in billions in the year 2013. The annual growth rate, okay, so this would be the growth rate that we have to add 1 to, basically, to figure out that base of the exponential function, which they actually did for us. So that's kind of nice. This situation is represented by the growth function p of t right there, where t is the number of years since 2013. Okay, so if 2013 hasn't passed yet, then the t should be 0, because no years passed. But if it was 2014, it would be 1. T would be 1. Okay, if it was 2015, t would be 2. Right? So we want t to be equal to whatever year represents 2031. Well, the easiest way to do that is just subtract 2031 from 2013, and you're going to get our t value that we're looking for is 18. So we are essentially looking for p of 18, the population 18 years after or since 2013. So this is going to be 1.25 times 1.012 to the 18th power. So the t became 18 in both of these spots here, as you can see right there. I am not going to expect you to do 1.012 multiplied by itself 18 times. So I'm just going to put this entire thing in my calculator, and I do expect you to do the same thing. If you do that, it says around to the nearest thousandth, so that's 3 decimal places, 1.459 billion. So that would be the population based on this model. Obviously things can change. It's just a model. It's meant to make a prediction. That's what the population of India would be if it was the same population rate. Okay, so as you can see, yes, there was a lot of words, lots to dissect, but they gave you the function. I'll make sure I do that too on the assessments, just to be fair, to follow the book. And then you have to figure out that you have to plug in 18 because we're looking for 2031. And then we got the value. All right, let's do the next example now. Writing an exponential model when the initial value is known. So that means we know what a is, okay, because the initial value is a. In 2006, 80 deer were introduced into a wildlife refuge. I'm going to write that down. 2006, there was 80 deer. Okay, by 2012, there was 180 deer. The population was growing exponentially. So if you wanted to, you can say, oh, this is linear and it's just growing by a fixed amount the entire time. But it's not. It specifically says that it's exponential. Most population does grow exponentially like this. Write an exponential function n of t. So now we're actually making a function. Before we were using a function to find a value. Now we have the values and we're trying to make the function. So this will be interesting. Okay, we do have the initial value, which is the value at the beginning, which is 80 in this case. So we have n of t is equal to 80 times whatever that base is, we don't know the base, of t. Okay. We need to figure out what b is. Once we figure out what b is, then we will finalize our n of t equation, that's what it's looking for. Write the n of t equation. So that is what we're going to do. This is a little complicated to set up. Now, since we have the initial value, this is pretty nice. So at t equals 0, so I'm going to write that over here, t equals 0, we have 80. Okay, and then here, this is going to be t equals 6 because the time jumped 6 years. So at t equals 6, the population is 180. So we can actually use this to figure out our b value pretty easily. So the first thing that I'm going to do is plug in 6, which is this value right here. And it's equal to 80 times b to the 6th power, and this n is population, the number of things. And in this case, it's 180. So I'm going to write equals 180. So now all we have to do is solve this equation for b. This is a b right here. And once we solve that, then we can actually finalize this orange equation up here, which is supposed to be the answer. So let's do that. First thing I'm going to do is divide both sides by 10. Okay. Next thing I'm going to do is divide both sides by 2. So this becomes a 9. This becomes a 4. So that means I'm going to divide both sides by 4 now. b is equal to, or b to the 6th is equal to 9 over 4. I'm going to raise this both to the 1/6 power, because if it's b to the 6th to the 1/6, it's going to cancel out the 6 and the 1/6, and you'll just have b. Should remember that from previous math classes. This cancels with this, and you're going to have b is equal to 9/4 to the 1/6 power. I don't know what that is. You're going to have to throw it in your calculator. Okay. It doesn't say how to round on this, so I'm just going to round to 3 decimal places. I'll try to make sure it says it on the quizzes how to round each time. So this is going to be 80 times. Now I'm going to do 9/4 to the 1/6 power in my calculator, and you're going to get 1.145. So I'm rounding to 3 decimal places there for the b value. Okay, so I threw this in my calculator basically to get that value right here. And then it's still raised to the t power, and that's our final answer. Okay, so if I plug in 0 for this, I'm going to get 80. If I plug in 6, I'll get about 180 because I rounded, so the answer is going to be rounded, but that's the answer for that one. And now we have one more, which is related to the one we just did, only this time we don't know what the initial value is. So this is going to be by far the most difficult problem to do with the most steps, but if you pay attention, it should be pretty straightforward. Okay, first thing I'm going to do is note that I am trying to look for a function f of x which is equal to a times b to the x power. That's the goal. I need to know what a is, and I need to know what b is. Then I have my answer. So that's what I'm going to do. First thing I'm going to do is I'm going to write f of negative 2. I'm going to write that a little better. F of negative 2 is equal to 6, because that's what this means. When x is negative 2, the y is 6. When x is negative 2, the y, which is f in this case, is 6. But I'm going to use that red equation up there to help me out. So I'm going to say a times b to the x, which in this case x is negative 2. Now we still don't know what a and b are, but at least we have some numbers attached to this. Because what we're actually doing is almost making an order of operations. If you remember that, we did that for linear. F of 2 is 1. Okay, from this, I'm going to use that red function again, so it's going to be a times b to the second power. Now from here, I want to solve for a and I want to solve for b. An interesting thing happens is if you divided f of negative 2 by f of 2, that means I'm dividing this by this. Those a's are going to cancel. That's pretty ideal because if the a's cancel, then we're only going to be left with b's, and then we can actually solve. Whenever you solve, you need to solve with one variable. So what we're going to do is we're going to cancel out those a's by dividing and solve for b. So first of all, f of negative 2 is equal to 6. F of 2 is equal to 1. I wrote that here and here, so that should not be a shock of where I got those numbers. And then this is going to be equal to, f of negative 2 is a times b to the negative 2, and I'm dividing it by a times b squared. 6 over 1 is 6. The a's cancel, and then we have b to the negative 4th power, because negative 2 and the squared there, you're going to be subtracting whenever you divide by those powers like that. And this is a b, not a 6. Kind of looks like a 6. From here, I'm going to raise both sides to the negative 1/4 power, because this is going to cancel with this. And then we have our b value. I'm going to write it as 6 to the negative 1/4 power, and I'll round at the end. Okay, but I'm going to need that value to figure out our a now. To figure out our a, you can use either that green equation that we have up top or that orange one. I'm going to use the green because it's just easier numbers. There's no negatives. You get the same answer either way, so whatever one you want to do, it's completely up to you. But I'm going to use this one here. We just solved our b, so that means we have f of 2 is equal to 1, which is equal to a. That's what we're solving for. But we just found our b, which is going to be 6 to the negative 1/4 power squared. Okay. Now from here, I'm just going to throw this entire thing in my calculator because why do all that work? It's just going to be a lot. So you're going to have a is equal to 1 divided by this whole mess right here, which is going to be 6 to the negative 1/2 power because you can multiply the negative 1/4 into 2. Okay. From here, I'm going to plug the rest of the values in my calculator. For a, you're going to get 2.449. I'm just going to round to 3 decimal places for that one. And for the b, you're going to get 0.639. So now we have our a and our b, which is what we needed here. So now we can actually write the final answer. F of x is equal to our a value times our b value to the x power. And hopefully you can read that. So that's a video on exponential functions. We evaluated exponential functions. We defined what they are, what they were based on their form. We solved some modeling problems with them. We created equations with them as well. So if you have any questions about anything in this video, let me know.